Welcome. In this segment, we'll be continuing our lecture on the general motivation for database. We'll begin by discussing the database approach in more detail. Recall that last time we mentioned the database approach as significantly differing from the use of simple operating system files. We begin this approach by properly designing a database. So that's precisely where we will begin this portion of the lecture. Next, we'll discuss the evolution of database systems. Life in the database world has not always been the way it appears to us today, so we'll trace a little bit of the history to see how we got to this point. We'll also talk a little bit about the database development process. So let's get started. In following the database approach, we start with a proper design. A data model provides a graphical diagram that captures the nature and relationship of data. Different individuals within the organization may wish to look at the data model from different perspectives. An enterprise data model provides a high-level view, simply emphasizing entities and relationships. As we drill down and look for more detail, the project data model provides such detail. So what are entities? Entities are objects within the application domain that are of interest to us. As we listen to a description of the application domain, we want to pay close attention to the nouns that are being expressed. These represent people, places, objects, events, or concepts within the application domain. These are the things that we represent as entities. The entities themselves are somewhat structured and consist of attributes, individual data items or properties that further define the entity. Relationships exist between entities. So as we talk about an application domain, we talk about these nouns that we hear being discussed, talking about the objects or the things within the application domain, but these things are associated with other things, other entities. So relationships depict some kind of an association between entities. These relationships have cardinalities. These could typically be one to many to many, or one to one. In our investigation of database, we'll show you how to create an entity relationship diagram, hence a data model to represent the components of an application domain. Entity relationship diagrams are used by analysts to conceptualize and represent the real-world environment. It's through the use of these models that we can proceed with the database design process. These diagrams additionally serve as a vehicle for communication between the data modeler and the business community. We mentioned the data models can have different degrees of information. Here we represent two data models, one showing kind of a high-level view, the enterprise view, and the other showing a project model, something more detailed. In the enterprise model, we show you customer, order, and product as entities, but we don't show you any real detail about them. We withhold the detail such as the attributes. But in the more detailed project model, we expand the information by including the attributes. So depending upon the individual, it may be sufficient to look at the enterprise model to say, yeah, that looks right, that's how our world exists. But as we're starting to build the database and build the application, it's going to be necessary to drill down and see more detail, hence the project model. A word on the notation here. In these entity relationship diagrams, the entities are depicted by these boxes or rectangles, and the relationships that connect them, showing an association, are depicted as lines. The attributes which describe further important characteristics of an entity are represented by the verbiage within the boxes or rectangles. Observe the relationship between customers and orders. This is what is called a one-to-many relationship. What it means is that a customer may place many orders, but an order is placed by one customer. The crow's feet symbol of the relationship line indicates the many side of the relationship. If we look at the other relationship between order and product, this is a many-to-many. A product can be contained in many orders, and an order contains many products. We have identified some relationships in our example model. Let's now take a closer look at relationships. First, we note that relationships may have different cardinality. We saw this in our example. Cardinality refers to the number of instances of each type of thing or entity that participates in a relationship. When a database is designed, a diagram is used to describe or model various aspects of the application domain. The diagram will identify things that are related as well as their cardinality in the relationship. The relationships and their cardinalities are part of what we call data semantics, kind of the meaning of what we're representing. Consider the relationship between customer and order. What does it mean to place an order? Is an order placed by exactly one customer? Is it possible for a customer to place more than one order? These questions and their answers define the meaning of the relationship, the semantics. Previously, we noted different cardinalities might exist. One-to-one, one-to-many, many-to-many. A database is a representation of the world, and some aspects of the world are quite complex. Hence, by providing an illustration or an entity relationship diagram, we can allow people to better understand this complexity. There are many ways to illustrate a relationship. When modeling an application domain, we'll be using the entity relationship diagram. Here's an example of a one-to-one relationship. The entity types are employee and parking space. An employee is assigned a parking space is assigned to an employee. So one employee is assigned one parking space. A one-to-many is illustrated here with the entity types of product line and product. One product line contains many products. Conversely, many products are contained in one product line. Thus, a one-to-many relationship can also be seen as a many-to-one relationship when viewed from the perspective of the other entity type. Although a particular product line may contain many products, when this relationship is viewed from the perspective of a particular product, that is, an instance of product, we say that a particular product is contained in one product line. And finally, the many-to-many, students and courses. Many students register for many courses. Employee, parking space, product line, product, student, and course are objects or entities in the application domain. What diagrams such as these do is to convey information about the relationships or associations that exist between these objects or entity types in the application domain. When attempting to understand something, it's helpful to trace back how we got to this point and what brought this thing into existence or fashion. The objective of the next several slides is to do exactly this. explain what motivated the development of database systems. The first computers were used in the 1940s. Database systems have been in use since the 1960s, running on large mainframe computers. In the late 1970s and early 1980s, database systems grew in popularity and availability. Although database systems are relatively new, the technology has advanced very quickly. Going back in time, we see that early programs were written in machine language or assembly language, and those that required persistent data used simple data files. But what's more important than that, this diagram tells us that the description of what the records look like within the file was embedded within the program. Furthermore, the program used input-output macros to interact with the storage device. The significance of the embedded data description is that these programs were highly data dependent, meaning that should the structure of the data record change, the application program had to be modified. Advancing in a timeline, we see third-generation programming languages and the operating system. In this case, the burden of communicating with the storage device has now been removed from the application program and placed within the operating system. The application program issues some kind of a read or a write request, which is handled by the operating system in terms of communicating with the storage device. Note, however, that the data description is still embedded within the application. Thus, a change in the structure or format of the record would require a change or update to the application program as well. Further in time, we see the introduction of the database management system. A lot has developed here. The operating system is still responsible for the low-level communication with storage devices. So with the advent of database systems, the description of the data file format is no longer embedded in the program. Should there be a need to alter the physical format of a data record, the program remains unaffected. There's no need to alter the code within the program. This is referred to as data independence. The DBMS has now assumed the responsibility of dealing with the physical format of stored data. This format information is preserved or maintained by the database management system and is part of that database system. In our figure, it shows the system catalog, that metadata repository, as residing on secondary storage. This is where descriptions of the records would actually be stored. So the application program then is in some sense immune to the change in physical storage. So the evolution of database technology has been driven by four main objectives. There's been a need for program data independence in order to reduce the maintenance costs. It is expensive to have to modify the program to make a change based upon a change in the data format. The cost in programs now is attributed to the programmer cost, not the cost of executing the program. Thus, these maintenance costs can be quite high. Reducing those is a real benefit. Another factor is a desire to manage more complex data types and structures. The ease of data access for less technical personnel, and this is one of the selling points of the relational model. We talked about the interface being application programs, but also the idea of ad hoc interactive query tools, and the need for more powerful decision support platforms. Relational database systems are common today, especially for business applications, and such systems have an easy-to-learn query language called SQL. And here we summarize the progress that has been made in terms of the evolution of database technology. In this course, we'll be emphasizing relational database. Let's consider both the software and the personnel that make up a database environment. Data modeling and design tools be one of the key pieces of software. There are automated tools used to design databases and application programs. These are referred to as case tools. These tools help to reduce the time and cost of software development, and their use tends to improve the quality of the systems developed. These tools are very useful in designing a database, that is, in developing an entity relationship model. They are also useful in recording some of the semantics that we talked about earlier. There are a number of tools that might be available, and one that's available within the Oracle environment at no additional cost is part of the Oracle SQL Developer Framework, the data modeler. Another component from the software side is what we're calling a repository here. This is actually referred to as a data dictionary. Much of the information that's contained within the data dictionary, the metadata, can actually be entered through a case tool. This becomes a reference for building the database, but also a reference for those using the database. The database management system. We've talked about this quite a bit already, and we'll continue to talk about this. This is the software for managing the database. And of course, the database itself contains our data. Application programs would be the software that uses the data stored within a database, and this could be done by writing programs in languages such as C or Java and embedding SQL statements that are effectively calls to the database to request data or to interact with the database in some way. An alternative is to use a user interface other than an application program using an ad hoc query tool. Some of these tools are text-based, some are graphical in nature. We've talked about both of these means of user interaction a little bit already. Let's tie these pieces of software together. With respect to the user interface, there are textual or graphical tools that fall into the category of interactive tools. Application developers will write programs in languages such as C or Java. Both the programs and the interactive tools communicate with the database management system, which processes requests against the database and returns results to the requester. Now let's turn our attention to the personnel. The data administrator or database administrator, often called a DBA, would be a person that's responsible for maintaining the database. System developers would be people who are responsible for designing databases and the associated software. And finally, the end users are sometimes referred to as business users or customers, people who use the applications and database. In general, a database can be considered as having three levels or views. The perception and understanding of a database depends on job function and responsibility. Thus, different types of users of the system include the database administrators, system developers, and end users. End users and application programmers tend to work with only a small portion of the entire database. These people look at the database from the perspective of the business data captured by the database. Hence, the view that they have is logical in nature. Programmers or developers create application programs. End users are people who use the system for business functions. Application programs interact with the database to provide functionality for use by the organization. The application program fulfills processes such as order processing, invoicing, payroll functions. Systems analysts and database administrators tend to think of the database in its entirety. Their view extends beyond that of a single application. Again, the perception is based on the business data content, hence such a view is also logical in nature. The system programmers may be more removed from the business data and more focused on the hardware and operating system files that serve to store such data. The interest that they have is more focused on how data are stored rather than on what data are stored. So the physical view reflects the internal representation of the database as it is stored in secondary storage using some particular database management system. How do organizations start developing a database? It's common to begin with enterprise data modeling. Recall that we compared the level of detail in two examples. One of these presented the theme of an enterprise model. Such models establish the scope and general content of the database. It effectively creates the big picture of data for the organization. It does not provide a design for any particular database. An enterprise data model includes the graphical depiction of the entity types, as we saw earlier. It also includes statements about how the organization operates. These statements are referred to as business rules. Developing an enterprise data model is just one component of a top-down approach to information system planning and development. SDLC, or System Development Lifecycle, is a traditional process for conducting an information systems development project. SDLC is a complete set of steps that a team of information system professionals follow to specify, develop, maintain, and replace information systems. Because the SDLC approach involves considerable time before a working system can be achieved, alternatives such as rapid application development have been used. A popular RAD method is prototyping. Prototyping is an iterative process of systems development in which requirements are converted to a working system. With prototyping, the analysts and business users work closely together. In practice, many projects combine various elements from SDLC and prototyping. In the next couple of slides, we'll take a closer look at each approach. SDLC is sometimes called a waterfall approach. Outputs from one phase flow down to the next. At any stage in the process, it is possible and sometimes necessary to return to a prior stage. This is called a cycle because it is iterative in nature. At any step, you may need to go back to a previous step. SDLC consists of 5 main steps. The first step is planning, which involves enterprise modeling. In early conceptual data modeling, this is high-level planning, most likely creating enterprise-level models, not project-level. Planning is followed by a more in-depth study called analysis. Data models developed here are more detailed. These are project level. And these include more entities, attributes, and relationships than appear within the enterprise models. Analysis includes detailed study, interviews, requirements elicitation, and document review, as well as studying the current system. Output from this involves a detailed set of specifications for what the desired system should do. Whereas analysis involves identifying what the system should do, logical design is concerned with specifying how the system is going to do it. From a database perspective, analysis involves drawing the various entity relationship data models, whereas logical design involves defining the tables, screenshots, metadata, and so on for the finalized system. After logical design comes physical design. This includes the development or acquisition of application programs. From a database perspective, we have decided on the physical database design and the DBMS, such as Oracle Database, Microsoft SQL Server, and so on, and written much of the SQL for creating and manipulating our data structure. Often physical design and implementation overlap. There is programming and more SQL that takes place during implementation. Other activities include installing the finished product on the production environment. Previously, it was in a testing stage. And additionally, preparing users through documentation and training. At the end of implementation, the system is said to be up and running. Finally, there's maintenance, typically the longest phase because this lasts throughout the lifetime of the operational system. During this time, there will be enhancements, bug fixes, and problem solving of various sorts. As previously noted, prototyping is a popular rapid application development method. It's an iterative process of systems development where requirements are converted to a working system. The system is revised through collaboration between analysts and users of the system. With system prototyping, a version of the system or part of the system is developed quickly to check the user requirements and the feasibility of some design decisions. A prototype system is used to show some key features of the system to the users. They can experiment with the prototype and refine their requirements before committing to high software production costs. The following general steps are followed when you take the prototyping approach. First, the problem is identified. Requirements are analyzed and a preliminary data model is developed. Note that through the process, both the requirements and the data model will evolve. Next, we develop the initial prototype. Here we move from the conceptual model to the logical model. Requirements are analyzed in greater detail. In development of the initial prototype, displays and reports are designed based on user input. This additional information provides deeper insight to the database requirements. Then we implement and users use the prototype. We revise and enhance the prototype as the needs are assessed. The database design may also evolve. And finally, we convert to an operational database. So prototyping takes a different approach to system development than traditional SDLC. It is less formal and more ad hoc, involving iterations of coding, using, and evolving. There is less emphasis on upfront planning and analysis and more of an experimentation flavor to the development process. Prototyping involves problem identification resulting in the initial requirements. Then a prototype is built. This prototype is used and refined iteratively for a period of time, and if the prototype works well, it becomes the de facto operational system. If the prototype doesn't work efficiently, it is converted to a more efficient operational system. Through the entire process, users are given something to work with. The users can provide feedback with respect to accuracy and usability. In this video, we continued with our lecture topic of general motivation. We discussed the database approach. In this discussion, we introduced important concepts with respect to database design. Our intention was to get you excited about designing a database. We'll have much more to say about that in future lectures. We also took a quick look at the evolution of database technology to better understand how we arrived at our current situation. Finally, we talked about the components of a database environment and discussed the database development process. In our next video, we'll wrap up our discussion of the general motivation. So until then, stay safe, and I'll see you soon.